Okay, I want to talk a little bit what's called about the central limit theorem. Central limit theorem is this idea we can use in statistics to determine if a distribution, a sampling distribution, is approximately normal. In the real world, we have a lot of distributions that are not approximately normal when we look at them originally. Oftentimes, they're not even roughly symmetric. They're skewed, they have multimodality, there's things going on with it that it doesn't look like something we're used to. What we can do is we can use this idea of what's called the central limit theorem to work through it. So what I want to do is I want to talk to you just about the basics right now. So what's going to happen now is I have a distribution here. If you look at this distribution up here at the top, distribution is clearly symmetric. In fact, I can tell you it's normal because it's defined as normal right here. It has a mean of 16 right here, mean of 16, and a standard deviation of 5. There's my 5 right there for my standard deviation. Okay, so now what's going to happen is I'm going to take a sample of size 5. So watch what happens when I do this animated version. This is going to take a sample of 5 scores from it. Watch what happens. 1, 2, 3, 4, 5. Okay, so what that did is it took 5 scores, and notice it ended up with 2 scores right here at about 16, 17, 2 scores here, 17, 18, and I think it's about 21. So what ends up happening is it took 5, and then it gave me an average 10 here. So these 5 black boxes are each of my individual scores. The blue box down here is the average of those 5 scores. So if you look at that and you were to try and figure out about that, if we wanted to say, what is the mean of this? What is the standard deviation of this? We would do 16 and 16, 17 and 17. So that's 32 and 34, 66. Plus 21 gives me 83. We do 83 divided by 5. 83 divided by 5 gives me what? 83 divided by 5 gives me about 17-ish. So it's slightly above the mean. Now what's going to happen is I'm going to do this thing 10,000 more times. What's going to happen is it's not going to really appear here. It's just going to appear down here. Watch. Okay, so now what's happened is I've done this thing 10,001 times. Done it 10,001 times. And it's told me that the mean of this guy is 15.99. Well, that's pretty darn close to the mean of the actual distribution. It's got a standard deviation of 2 as opposed to a standard deviation of 5. The reason that this is happening is as follows. This is the reason it's happening. There's less variability to this blue than there is this black. This black is the actual distribution of everything. The blue at the bottom is just the average of 5. So I've done 5. I've done a sample of 5 over and over and over again, 10,001 times. So there's less variability the larger my sample size. But as you notice, it's still centered at the same place. It still has that approximately normal shape. Okay, so here's where we deal with in the real world. I'm going to go ahead and clear everything out. And what I'm going to do is I'm going to make a skewed distribution. So now what I want you to look at is I want you to look at this skewed distribution. It's definitely skewed to the right. It tells me that the mean is about 8 and a standard deviation of about 6. Now what I'm going to do is I'm going to show you something. I'm going to make the first one a sample size of 2. I'm only going to take 2 people out of that skewed distribution. But down here, I'm going to take a sample size of 25. So what that means is I'm going to be taking an average of 2 out of it. I'm going to be taking an average of 25 out of it. And what I want you to watch is I want you to watch what happens when I go ahead and I take this sample a few times. So I'm going to go ahead and just do it 5 times. And I'm going to do it another 5 times. And another, and now we'll do it 10,000 times. What I want you to do is I want you to go ahead and I want you to look at what happened with this skewed distribution. Notice there's still a skew to the sampling distribution. There's still a skew there. Okay, what I'm going to do now is I'm going to show you what happens when we do it with the 2, and we're going to do it with the 25. So we're going to do it with both. Sample size 2, sample size 25. We're going to do it 10,000 times. I want you to look again. There's that thing where we looked. That still has a skew to it. But when we get up to 25, look what happened to the shape of that distribution. The shape of that distribution no longer has a skew to it. It actually has more of a symmetry to it. In fact, it is approximately normal, it's approaching approximately normal. And what I want you to notice is I want you to kind of take an idea of, look what happens in terms of this. The means are still about the same. The centers are always like the same, the real answer. But the difference is this guy right here, standard deviation, it gets smaller, but it still stays relatively large at 4.4. It still kind of shows a little bit of skew, but as we go to that larger sample size, what happens is that larger sample size shows me that I get more and more symmetric, so therefore I get closer to normal. So the whole goal in this process is what we've done when we looked at this other sheet, kind of walked through it, was if we have a distribution that we don't know the shape of, we have to assume that it's not approximately normal, and then we can use what's called the central limit theorem. The central limit theorem tells me as long as I keep a sample size of 30 or larger, I know it says 25 here, but the number is 30 or larger, I can describe the shape of the sampling distribution as approximately normal. So